last session of the day with Professor Michael Sachs, who will be talking about neural network Feynman approach for cardiac simulations.
Thank you. Thank you. Thank you for this kind invitation. I really have enjoyed the meetings. What I want to talk to you today is, so we have until 4 o'clock?
3:45.
What's that?
3:45.
Okay. 3:45? You said it's 30 minutes? Okay, all right. Boy, you can never trust these guys. Anyway, so this is some stuff we've been working on. We started about 5 years ago, and on trying to develop alternative methods to do finite element modelings of the heart and the valves to get around some major problems. And I'll just kind of go through the background fairly quickly. So obviously, you know, there's this organ in your chest called the heart, and it pumps the blood. And it's a very complicated beast, multiple chambers, valves, lots of tubing, lots of plumbing. For those of you who have a fluid mechanics background, you may object to the fact that the flow goes down and comes back up in both ones, and it's a very strange beast. But it works, and generally it works pretty well. However, the main area that we're really interested in is the interaction between the left ventricle and the mitral valve, and this is really what's, and particularly what's called ischemic mitral regurgitation. Now, those of you who have ever tried to read the clinical literature and take a look at it, their terminology is bizarre. It makes no sense. And they have things like organic regurgitation, and we don't follow that. But the one we're really into is what's called secondary. And there's functional and so on, but really, it's really a disease of the ventricle. And what happens is that the mitral valve gets pulled open because the ventricular wall dilates, and you get ischemia and all kinds of, from the ischemic areas, and then it becomes regurgitant. And this is closely related to work, I think, to several people in the audience who do work on coronary systems and looking at this. And so our focus is not so much on the vasculature, but it's on the ventricle and really what the effects of the ventricle on the valve. Now this may look to you upside down, but you have to remember in anatomy books, the heart, that's why the valve part is called the base, and this is called the apex, even though it's upside down. But the basic idea is that it's this tethering problem, and so we're trying to figure out how to do that. Now, the cure for it, or really the treatment, is an older method. It's called undersized ring annuloplasty. It doesn't look terribly sophisticated because it isn't, but it's really a way of surgically implanting a rigid ring or a flexible ring that actually brings the annulus, the size of the valve, down. Highly invasive, not terribly successful. A more recent one, it's been around for maybe 15 years, is called the clip, the mitral clip. And it actually it's inserted transcatheter, using a transcatheter delivery approach, can actually clip the leaflets together, and surprisingly quite effective. But still has about a third recurrence after about 3 years. And nobody knows why, and at this time nobody can predict the outcome. A couple of my CSIM students, Kenny Meyer back there, actually goes over to Dell Medical School, and we've watched them do this, and it's quite an experience. So what we really want is a predictive clinical tool. Now, when I say there's a distinction of what we're trying to do from what a lot of other people have done, we're not trying to just study this as a simulation project. We're trying to develop a clinical tool that clinicians can use to predict what's going to happen for this patient, as opposed to doing an academic study, which is the way I was brought up. But it's very difficult to do because there's so many factors that involve with it, and there are many questions, and if you try to figure this out through, say, large clinical trials, which is the way most clinical projects are done, it doesn't work. Now, there's been many, many, many years of cardiac simulations. We're just one of many people who do it. There's the Hunter group. Peter Hunter is one of my personal heroes. He was here last week, and he was the one who really helped develop realistic models of the heart. Natalia Turovna at Hopkins, for example, does really wonderful work on electrophysiology, but they're all have completely different ways of doing it. There's no, there's the data, how they do it, what they represent, and so on. It's very difficult. So we developed a model using a single data source with a single LVMV model. This was done with an in silico project funded by Medtronic a few years ago here at UT. And the short of it is basically we took an ovine heart, and I won't go through all the details, but we were the Medtronic did for us at the Visible Heart Lab at the University of Minnesota. They got the whole thing, and they got the LV pressure and volume, the action potential waveforms, the electrocardiography, and many other things. We actually excised the heart, put into MRI image. It got the geometry, got the diffusion tensor, got the fiber structure, got the whole thing. Everything's registered. Everything's in the same heart. And those of you who ever want to do this, you're welcome to, you know, but it's a lot of work. And this is just an example of a pipeline of everything that goes into developing, say, even a standard model, which uses, say, Abacus. So it's just quite a bit of work. Now, after a result of all that, we've actually developed a very high fidelity ovine. From all that data, we developed a very high fidelity LVMV model with a mitral valve in there. You can see we have cords and so on. And there's all kinds of subtle things that you have to do in this. It's not just create a model and mesh it. There's quite a bit of calibration and work that goes into it. Now, the main thing we did is to look at the effects of infarcts at different locations, and we can compare this against what goes on in the literature. And we're able to actually do this quite nicely and be able to show, for example, that an infarct in this location has certain effects. And then when we put this into the LVMV model, I don't know if you can really see there's a little opening there. It's all you need to make the valve regurgitant, and that's very bad. It produces congestive heart failure. It actually can lead to right heart failure. It leads to atrial defibrillation. There's many, many negative things. So we're able to actually do that. So we're all very excited by this. The problem is that, well, what do we need a new approach? Well, you want something that's rapid, that's accurate, that's detailed. It needs to be robust. The current methods are very slow, okay, even on high-performance TAC computers. They have many hours to simulate. And many people ask me, particularly here in the Oden Institute, with its rich faculty in mathematics, say, why don't you reduce order models? Reduced order models don't really work for us because the potential loss of accuracy and don't really capture patient-specific features. So it's not really an option. So we need something new. And then so what we developed kind of along the lines of the old what's called the deep Ritz methods. And by the way, for those of you who don't know, people have been solving PDEs with neural networks since at least 1998, possibly earlier. At least that's the first paper we were able to dig up. What's that? 93. Thank you. Can you send me the reference? I would appreciate that, because every time I talk to somebody. Okay, not 1833 though. Okay, all right. Okay, I just want to make sure I got my century right. So, but anyway, but you know, I got this. For those of you who kind of wonder where do you get these ideas, it's sort of like it was from a biomechanics meeting in Hanover, Germany, right in Jan's hometown, it was an actually interesting one where somebody was actually just taking a cube of isotropic hyperelastic materials and deforming them, and says we can solve it using collocation methods using this deep Ritz method. Basically, it's just solving an energy equation. It hit me like a ton of bricks. I God, what a great idea. And I'd never heard of it. And just to be clear, and I don't want to get into the pans, the pins, all these arguments about what do you call it. It's not pins. Pins is really mainly if you have data, and the idea of using neural network solved PDEs, like I said, is very old. So what we call it is basically this. We learn families of solutions over ranges of boundary conditions. We use the finite elements, not the finite method, to perform the mapping, define the boundary conditions, use numerical integrations, all the standard stuff that we all know and love. The finite method is not used for training, and there's no actual global stiffness matrix or anything like that. And it does not require experimental data or finite element simulations. Okay. Now, what we tried it out is say, can we do this on a functioning heart? And that seemed to be fairly demanding, but the idea now is not to train one point or even a single pressure volume loop, but if you actually fill the heart passively, you have something called the end-diastolic pressure volume relation. It comes back from my graduate days taking many medical courses, and the thing you learn is all the jargon. and then you have, if the heart was a complete tetany, totally contracted down, and you filled it with blood, you would get that relation between pressure and volume is called the end-systolic pressure-volume relation. Everything within those curves represent the entire functional range of the heart in that current state. And of course, in a real heart, it uses pressure volume loops to go over the cardiac cycle. So we want to train over that entire state. So with the way we did this, we started off with a prolate spheroidal geometry just to make things easy. But with fairly realistic boundary conditions and geometries, and there's, it's about 1,500 elements, about 540 nodes, and then these are the boundary conditions that we did. We actually did a realistic fiber structure. It's prescribed, but it gets you something reasonably good, okay? And then, of course, the way the method works is that we're actually satisfying the total potential energy of the system. That's what we're minimizing. So this is the internal mechanical energy, the body forces, and the surface tractions. And the way we use the neural network learns this solution to minimize this function, just like conventional finite elements. And if you want to go a little bit deeper, we actually have this a little bit, getting a little more formal way to represent it. And then we can actually come up with this potential function. Now, the way we train it, this plot actually I think shows it. So we would have, for example, for our general soft tissue model, we would have some history of displacements or whatever boundary conditions you want that we would want to train over. That is fed into the input layer of the neural network and whatever design. And I will say the neural networks for these things are fairly modest. They're not very large and not very complex. The output layer is the displacements of each node in the finite element model. This is put into a processing subroutine where we can now compute the total internal energy. That's fed into a training regime where we look over all training points and then basically wait till we converge. So our training is really training on that system. Okay, so just for your case, you want to know, it's an orthotropic Fung type model. This is all pretty standard hyperelastic stuff. This is the Hunter-McCulloch-de-Kurs model, which is a very standard phenomenological model for muscle fiber contraction that includes both a prescribed, it's called calcium, it's based on the calcium, but it's a fiber force level, and then this term here modulates the amount of force based on the fiber stretch to capture that response. And then everything else is pretty standard, nothing new here. And then again, we have a passive model, we have an active model, and then we add them up to do it. So this is pretty standard. Now, the way we model it is that we start with here, the mitral valve closes, isovolumic contraction. We can do a pressure volume, AV closes, go down, and so we don't train over a pressure volume loop, but we can imitate one. That's the key thing. Okay, and then again, it's bounded by these two bounds. Now, what's really cool, if you take that, and this was one of things that we thought of that I thought was really cool, because we're not really simulating the heart directly initially, we can actually train over the pressure, the fiber stress, and the volume over a single. So this plane here represents our actual training space. Okay, and you can see this is what the pressure volume loops look like when they're mapped onto that space. So you go from here to here. And so we need to train over all of that. And actually, and again, we then train over the domain mapping, and everything gets mapped into the displacements. So actually, what you end up learning, by the way, is the displacement field. Okay, so again, everything else follows. I won't spend too much time here. It's all pretty standard by these days. Neural network training, just minimizing some functional. Now, what made this a little complicated, we had to actually, even though there's a potential energy, but because pressure in the wall moves, okay, you can't define a potential function, and you need to use virtual work. And so we actually went through this rather elaborate process to define using standard virtual work here, and then we can actually now minimize the virtual work for each step, and we go through the whole analysis. Actually, with my graduates, we worked it all out. I hadn't done that since my undergraduate days. But we actually develop a residual vector, just again like in the this conventional finite element method, that we basically minimize the residual of the virtual work, which is basically the same thing as the potential function. And then if you looked at it a little bit more formally, I don't really have a lot of time here, so I'll just kind of skim over it. Again, it's all the same basic equations. And then we develop a weak form formulation, as you can see here, okay? And then we actually integrate it. And then just go right through the final equations here. And then finally, we have a external work, and then we have that's the internal, external, which is the body forces and external tractions, and we just put them all together and sum them up, and then we find the minimum of that. Okay, and that's just a very standard way of doing it. Now, in our case, we do the same thing as I showed you before, only now we pump it into this residual vector, compute that, and minimize that for all the data points that we need to train it on. So it's really pretty cool. We did everything in JAX. I think most of you probably know what that is. And has a number of nice features, including automatic differentiation, automatic vectorization, just-in-time compiling, and all that stuff. Now, in terms of some details, it's only 3 hidden layers, 1024 wide, so it's not a very complicated network, using the atom first-order adaptive gradient. And basically some of these other details. We have an adaptive learning rate. It's trained over 3 A100 GPUs. And this first early version took about 36 hours to train, and we got it down later on to about 50 minutes with a number of improvements. Okay, now here's the reason part of you do it, we can improve it, is that these are the 15 training points to train the whole model. And we can fine tune it a little bit, but we then map, once we have the model, we can map the pressure volume loops, and then you get that. And let me just see if I can. There we go. So actually, so the red dots are the red dots are the Phoenix conventional finite element simulations, and the blue mesh is the neural network, and they're like extremely similar. Difference is only about 0.06 millimeters, so it works quite nicely. Okay, so it's accurate. And then if you actually look at the neural network finite element and the finite element solutions, say for the Lagrangian strains, they match up very closely. Same thing for the second PK stresses, again, very closely capturing a lot of subtle detail here, which was amazing how well this works. Now, the next step we wanted to do is to say, okay, can we use this to model a disease process? And of course, we go back to the infarcts that we looked at before, and we came up with this modified model where we actually model an infarct here, and you can see there. And then we actually, our training now is putting a set of infarcts together in various locations, and then training it over that so we can pick an infarct anywhere in the heart and say, can we predict it? That's the basic idea. Again, we had to expand, made a finer mesh, a bit more involved neural network. Much of the rest of things are long. It still took about 7 days to train. We're still in the process of, we're finding that this, again, is from a very early stage model. And then, of course, the training goes down just like what you want it to. So it took about 1 million iterations, about 5 million. And then, so it solves a parametric, actually, let me, I know what it is. So I'm actually able to get those results. There, okay. So there's the animation now of the infarct in a different location that leads to training, and these are the results of the error, which are generally very small. Okay, and it's actually able to reproduce all the dyskinetic features of the infarcted heart, again with a randomly chosen infarct. So it actually can work quite well for these sorts of things. Okay, now, oops, there we go. Okay, so just summarize, we're able to do it. The training process, again, doesn't rely on that. The key thing we're doing is we train over the entire functional space. So this is actually very important. Eventually, we want to be able to train this on different geometries and boundary conditions and so on. And the other thing, too, is they can do a complete pressure volume loop in about 1/3 of a second. So it's the computation performance. And this is just on our modest rack system. We're not using any of the TAC computers. Okay, so where we're going to next is we can do this with conventional elements, is using NURBS. Being here in the Oden Institute on the same floor, Tom Hughes for over almost 14 years tends to, you kind of think in terms of splines. Everything, the whole world turns into a spline. It's sort of a disease, but it actually works quite nicely. So again, we have everything is mapped to parametric domain. We try to tri-leaflet valve here. Same type of pipeline, but now the output layer is no longer the nodal coordinates, it's the control points. And that's fed into the NURB system and fed back in, but the basic error process is the same. Here's some example of a tri-leaflet valve being loaded, and this is the displacements with a conventional finite element and the neural network. It's quite nice, very close. We just can also change the fiber structure of the leaflet and have all these perturbations. It's really nice. We then had to add contact. This is the work of my former postdoc, Christian Goodbrake, and Kenny Meyer. And we basically weakly enforce energy penalties, sign distances are then used. And then he was actually able to start off with some simple contact using like Hertzian contact, and eventually build it in for a full multi-body contact with three leaflets. And it actually works pretty well. And if you can see that, but when you have three leaflets together in a valve, they can, because they're kinematically free, they can twist. It's called pinwheeling, and this actually was able to reproduce it. And it took about 2-3 seconds to run this. So it's pretty cool. I don't know, when are the posters? Tomorrow? Tonight, yeah. So if you want to see more about that, see Kenny's poster there. This paper came out in IJMBE earlier this year. It's a very nice work, actually. Now, for those of you who kind of wonder, what kind of performance you get, this, I think, is shows two things that I think this method and lots of other methods out there that do related things. If I take a conventional finite element simulation and I increase the degrees of freedom, of course, it goes up. Now, for those of you in my generation, 75 seconds to perform a complex three-dimensional valve model with contact is nothing. I mean, but if the neural network fundament does it in about 3, but what's interesting here is the neural network fundament is essentially flat. Okay, so once it's trained, the computational time it doesn't really matter, and not really a function of problem size. So I thought that was very encouraging. But you would expect that. So overall, you can see the model, what we call the surrogate model, can provide these simulations very quickly. It's essentially, there's no loss of accuracy. It has all the details of a conventional modeling approach. And we can train over a family of solutions and ranges of boundary conditions. This is, I think, very important. And it's fully different. It's a fully differentiable map, and makes so all the computations are exact. There's no approximations. Now, let me just say this just to wrap up. While I really love this approach, it's really intended for what I call mini query problems. So if you have a clinical problem and you say, here's a reconstruction of a patient's heart, what can I look at hundreds of different type of surgical procedures, or a procedure of this particular one, the best way to do it? It's really ideal for that. But there's always going to be a need for conventional forward simulations where you just have a problem, we want to run it. And we've looked at over the past year on Ben Thompson, one of my other CSIM students, has a poster showing what we've done using what we call Cardiacs, which is a refactored version of JAX-FEM. And we can now have really phenomenal performance improvements. This is not a neural network approach. It's simply using JAX to replace the conventional finite element codes, and it's very promising in terms of being very high speed for when you need that for that. So they're very complementary, and they're built on the same library platform, so there's a lot of overlap, which is good. So where we're going next, just to kind of wrap up, we're actually working toward LVM. And actually doing an LVMV model is very difficult because the modality to reconstruct the heart is usually MR, sometimes CT. Valves, it's ultrasound, okay? And registering and doing both at the same time is very difficult, if not costly. But my collaborator, Allison Pouch, and I are working together on these combined LVMV models. And then we also want to go the other way, which is getting down to biophysics. And this is some very nice work where we want to get down to more realistic models where we can map these models, map this information in, if you heard us all talk about before, the more information you can bring into your model, the more high fidelity it'll be. And so I've done also work in this area looking at multi-scale models of myocardium, and myocardium is really hard to work with. Okay, and electrophysiology, we're actually starting a collaboration with the Quattroni group at Polytechnico Milan, who are probably the best in the world at this. And just want to thank funding and the really whole group of people who do this. They just make me look good, like I know what I'm doing. So thank you very much, and look forward to any questions.
Thank you very much, Michael. And floor is open for questions. Questions?
Nice talk. How do you pick the size of the infarct when you're modeling that?
Well, the infarcts can be actually detected and mapped out clinically with MR. They can get a pretty good idea, so you can do that. But the issue really is, in that case, is not just where it is now, but where it's going. Because as you know, the clinicians try to keep that border zone, and that's where you really want to go. So that's where we're trying to go. So the question is, it's like how bad will it get before we can't do anything about it? That's a very hard question for them to answer, and those are the kinds of things that we can do. These Oden model infarcts we kind of call them designer infarcts. The Gorman lab at Penn, for many years, that was their claim to fame. They could actually design the precise type of infarct, basically exactly where they put the snare on the descending coronaries. That's it.
I have a question. For incorporating clinical data, what do you think is the sample size that you will need from, because in the simulations you can run as many as you want, and it's very well informed.
Yeah.
But even then, there might be still some.
Well, it depends on the application. For the mitral valve, where we have a very well, I don't say it's well established, but we have an established pipeline now to do exactly that. We start with clinical ultrasound data, nothing special, just conventional transesophageal ultrasound, and we can create a highly calibrated, a calibrated predictive model for that. But that's based on 15 years of studying mitral valve mechanics. The heart is more involved, but it's more about getting the geometry and then using templates and pull. That's why we looked at the LVMV. That's why we're moving on this to get that, because just getting that data and then we build the models in that. So you can get a lot. So you have to get the geometry and it has to be mappable, and then you have to get the physical characteristics of that heart, and then be able to, once you got that, then you can do the predictions. So there's still, for the valve, we're very far along. The heart's going to take a while.
Right.
There's a
one quick question. Yes.
Thank you. I want to ask about the segmentation of the geometry of the heart and to what extent it can be automated. How much do you have to do manually to segment?
Well, I don't have to do anything. I just tell my graduate student, go do it. It's easy for me, right? No, we're moving. In fact, Kenny Meyer there, sitting there quietly trying to avoid attention, is working on we now have a semi-automated pipeline. I love these terms are academics. Semi-automated means the grad students do it. Automated means the undergraduate do it. Manual means nobody does it, right? But basically what we do is we're moving toward a completely automated pipeline. So we can read it in, and it runs right through and develops a calibrated model in about an hour. And that's quite realistic. But because we know what's involved, there's a lot of background information and experience it takes to get it to that point. Cardiac models, I think, segmentations in geometry, but the biggest challenge is still creating a high-fidelity cardiac model, not just the geometry, the fiber structures, the physical properties, the electrophysiology, on a page-specific model. That's still the goal.
Right, let's thank Michael once again.
Okay.